This is the first part of a three-part series on PSpice circuit simulation. This first part, a general introduction and a demonstration of usage of PSpice in power electronics. My name is Chris Iannello. You can find out a little bit more about me on the bio link, but my contact information is shown here at the bottom of the slide, so feel free to contact me with any additional questions. We'll start by, at a high level, describing everything that we'll cover in the next 15 to 20 minutes. In part one, again, a general introduction. We'll talk about what SPICE is, what this particular variant of PSpice is about, variant of SPICE, PSpice. We'll talk about how to get the demo version that I'm using in these videos, as well as its limitations. We'll go through some useful links for online video training and some examples, and we'll go through a very interesting, I'd say, and a very comprehensive documentation interface, which is a great resource for learning. We'll talk about the piece parts that make up the PSpice tool workflow, what pieces of software you touch as you go through the simulation process. We'll also get into kind of some fundamentals, like what is PSpice most commonly used for? What kinds of simulations can you run? And then we'll wrap up with a quick demonstration of its usage in power electronics. SPICE, the simulation program with integrated circuit emphasis, was envisioned to be this general purpose open source analog electronics simulator, and it was intended initially to have an integrated circuit focus for the design of integrated circuits. It was developed by UC Berkeley in the 70s with a variety of variants. The most popular, or I would say the one that was gaining the most popularity, would be at the SPICE 2 point, when they provided a number of different simulation types and a fixed time step for the solution. Now, this is an early example of how successful open source software can be, in that UC Berkeley wisely pretty much gave this software away. And that inspired and served as the basis for many other circuit simulators. The most prominent commercial versions now, PSpice and HSpice. We'll go through, of course, PSpice here, the one owned by Cadence Design Systems. I should note that the integrated circuit industry really adopted SPICE quickly, and there are still SPICE variants that are custom built by some semiconductor manufacturers. Others don't base their circuit simulation on SPICE, but have similar programs. So that's, of course, very popular. And we should note that SPICE was named an IEEE milestone in 2011, so certainly something that's had an impact. Now, SPICE at its core includes three analyses. There are a number of analyses that it includes, but the core analyses that we look at are the AC analysis, the DC analysis, and the transient analysis. And we'll talk more about what these are when we get into PSpice itself in a subsequent part of this series. Now, what's it most commonly used for? Well, the schematic capture front end, which is a product called Capture, is probably one of the 3 or 4 most common industry standard PCB design tools. So that's how you enter your schematic if you want to lay out a board. And most fabrication houses accept those sorts of files. Now, PSpice as a mixed signal circuit simulator, when I say mixed, I mean mixed analog and digital, or straight analog simulator, is probably one of the most, if not the most common of that sort. But you just see less analog simulation these days. So I would say you'll certainly encounter capture drafted schematics very often in the aerospace industry, and you will occasionally, but less often, encounter PSpice circuit simulation. PSpice users today are usually analog designers of some sort, or a power supply designer for the most part. And it's less common when you consider that microcontrollers, PLDs, various PLDs, FPGAs, etc., microprocessors, they really can't be simulated in this package readily. There's useful links here for additional information. The light version is downloadable for free from Cadence. If you click on this link, you can get there. If you do that and you install the software, well, let me take you to that link. This is the page that it takes you to. You can download the entire product suite, or just Capture and PSpice only if you don't want to get into some of these other tools. I have the entire product suite on my machine, and so if you go to All Programs, Cadence, you'll see under 16.5 Lite all of these programs, these applications. Here's Capture, PCB Editor, PSpice, and PSpice Advanced Analysis. There's also a number of tutorials. If you click on the README file, up will pop this, which includes the limitations of the Lite version. I should point out that it seems like there is a lot of limitations. There's no expiration date on that software, but in terms of physical size and the types of parts you can use, you are constrained. Now, in my experience, it's not a strong constraint. You certainly couldn't design a commercial product, and if you really wanted to do a complete and thorough analysis of a power supply design, for example, in many cases it would exceed these limits. So in that regard, it's effective at dissuading professional uses. But it's still a very useful tool. The Lite version is a very useful tool to getting the core understanding of a circuit topology down and the fundamental functions. So I encourage you to use the Lite, download the Lite functions, the Lite software, and use it because it's very useful even in the Lite limited version. Okay, back to the circuit simulation presentation. There are also a number of links shown here that are basically additional online videos that can help you further your study. Now, how to use that integrated help. This integrated help environment really covers all the tools. That's the first thing that I love about it. You'll notice there are other packages like that. MATLAB and Simulink will take care of that to some degree, or if you use microchip microcontrollers, they have something similar as well. But what they don't generally do is a single search covers any PDF or any Windows help file on your machine, and this search will do that. This single search will look through any help file as well as any of the numerous PDFs that get installed onto your local hard drive during the normal typical install. So it's a fantastic tool, and I won't go through messing with it, but if you type SBreak into Cadence Help, and by the way, you can find it right here under All Programs, Cadence Help. You can do the same search that I had, type in SBreak, which is an idealized voltage-controlled switch, often used to mimic the function of a MOSFET. And you see all the entry points. If I click on this guy right here, I'll bring up the PDF, and I can word search and find everything that I need. So it's an excellent tool. Now, what are the piece parts that make up PSpice? The tool workflow. The first tool you'll encounter in this workflow is Capture. Now, while the original Spice took text files as their input, nodal netlists basically as their input, modern simulators use schematic entry front ends to allow a graphical description of the circuit. Now, these schematic entry front ends don't just accept the schematic, they also have some computational horsepower behind them that allows them to output files that describe the electrical interconnections of the circuit, as well as footprints of the part packages, as well as physics-based models of those parts, so that you can feed that data, that raw data, to say a circuit simulator application or a board layout application or some subsequent tool in the workflow. Now, Capture is a common entry point for most any workflow in the Cadence family of tools, whether it's simply rendering a schematic or doing a board design, doing a simulation, or even if you're generating VHDL for a PLD design, that's where you start. Now, when used with PSpice for simulation, the options that you pick during the new project wizard, which I'll show you in a subsequent part of this series, it ensures that all the visible parts in the libraries that you can draw from have a simulation template. Now, this is a common pitfall. Most parts that exist that can be placed and visible in Capture do not have Spice templates, and as a result, they're not simulatable. You should consider that this tool is supporting board layout as well as other features too, not just PSpice, so keep that in mind. It's a common mistake. Now, after all this, Capture generates a series of text files and passes them to PSpice. These text files describe the types of simulation that you want to do, and it also describes your circuit as well as the electrical models of the parts within it. And this is what it looks like here, and we'll go through an example of simulating this circuit at the end. We see the various pages here across the top, and then across the right-hand side there are the part templates here, where we basically apply parts and we lay out the parts and lay out the wires and such. So basically you draw from these templates here. Across the top there's the menu bar, and if you see basically 4 scope probes with green letters there, that bar, that entire bar, is your simulation control bar. It only appears when you pick the right kind of project in Capture, so I'll show you that in a subsequent part of how we go about generating these schematics. Now, PSpice. PSpice is automatically called from Capture when a simulation is started. Modern versions of PSpice integrate the viewer as well as the Spice engine and options for controlling the simulation all into a single application. It's kind of like a very capable digital oscilloscope, and I'll show you an example of that here, where you have basically a number of traces. This is what these plots are called, along a number of plots. Each line is a trace, each plot is a set of axes, and we have basically measurements along the bottom. Now, what kinds of simulations can you run? From the Capture Simulation Profile dialog, you see that the main analysis types are the ones that we've expected and that were there all the way back in SPICE 2 from UC Berkeley. Time domain transient, a DC sweep, an AC sweep, and a bias point. Now, this commercial package, PSpice, adds a number of variations, a number of add-ons. You can do various Monte Carlo worst case analyses, parametric sweep, temperature sweeps. And then in the advanced analysis light, you see at the lower part of this window, there's sensitivity, optimizer, Monte Carlo, and smoke. In this series, we'll focus on time domain, AC sweep, and bias point simulations. And if we have time and if there's interest, I'll run a Monte Carlo and an optimizer simulation example in a subsequent part of the series too. So we're up to our demonstration in power electronics. There'll be another series in power conversion principles and DC to DC converters that we'll talk about. So for now, just accept that we won't talk about flybacks or forward converters specifically, but we are converting DC to DC. We are showing a DC to DC converter in this example. It's an actual converter design of a commercial grade product, so I've modified the design such that breakout parts are used. Breakout parts are general demo parts. They're kind of the generic versions of diodes and transistors and such, so you'll see that there. Fortunately, they also simulate faster and are somewhat more ideal. Now, a couple things. In this example, we'll probe a few nodes so that we can see different values, and we'll also do a load transient study. And if we have time, we'll continue on and do a few other example studies on this demonstration. So now going over to the tool, I have the schematic loaded already. The simulation profile for this particular simulation is a time domain transient. It's to run to 0.6 milliseconds or 600 microseconds. The maximum step size is told to be, we're telling it could be no more than 10 nanoseconds, and we're telling it to skip the initial bias point calculation. We'll click the green button and say go to do the simulation. And when we do, we can go over and open up PSpice. We see that in the lower right-hand corner, the simulation is progressing. There's a percentage, and then we see basically the total time here. What pops up is a variety of plots. Each one of these plots has a number of traces on them. They happen to be whatever I was showing last time when I did the simulation. I'll go to full view so you can see the simulation as it progresses. And this is the PWM signal that's applied to the drive. It's the voltage of the drive node at the top plot in green. And we see in red on the third plot down the inductor current here, and I'll highlight that. So this gives you some examples of things you can see. Now, if I don't want to see the voltage of the drive node, I will delete that from the top plot. I'll select that plot. I'll go back to Capture, and then I'll grab some of these markers. Let's say I wanted to see the output voltage. I'll probe that marker. When I do, I'll right-click and say End Mode. When I do, the marker will actually show a color, and that color is representative of the color of the plot that we've just added, the trace we've just added in PSpice. Now we'll quickly do a load transient study. One thing to note, if I wanted to, for example, look at current, current is positive into the node. So if I want to look at the inductor current flowing into that node, which would be positive, I'd click there and add that marker. Has to be at a terminal for a current marker. Notice it turned red, and you see that there's our inductor current here. Now lastly, we'll just quickly do a load transient study here. I will add a part. I happen to know that the time controlled switch is switch T close. I'll type it up there in the text window. It'll attach to my cursor. I'll touch R to rotate it. I'll place it on the schematic. I'll right click and say end mode to get that part off of my cursor. I will add a resistor, hit R to rotate it, connect it, and we can see that it's ready to connect when the red dot appears. I'll go to the right, click place wire. I'll come around and wire that in parallel. And I will put a 10 ohm resistor in parallel. And this is the time to closure. I'll set that to 400 microseconds. U is micro in PSpice speak, so that's an important thing to notice. And so now we have a load. It's running at 3 and will be running stable that way for 400 microseconds, at which time we will parallel end 10 ohms and the load will go up. I'll run PSpice with that in place. Go back over here to the circuit simulator. We see, looking at the lower right, that it's progressing. It's up to roughly 100 microseconds. If we have a simulation convergence problem, it'd appear here and we have to troubleshoot it. But this example has no such problems. At 60% complete now. And now we see at 400 microseconds, we should see our transient appear. Which we do, and if we zoom in on that, zoom fit, we can do a zoom area, which is what we really needed to do. And I scroll in here, I see that if we change that axis, let's take the inductor current off. You see we can just delete it right here in the window. We can change by double-clicking on the axes the values here, and instead of going to 0, I'll go to 25 to 35, and we'll do here, we'll do 29. So we see this is our load transient, and we dropped all the way down to, we'll toggle the cursor, we dropped all the way down to, and we got to look at V output down here. Uh, 25.8 volts from approximately 28 volts. So that was our load transient. Zooming back out, and there's back to our overall output voltage. So this is an example of the usage of PSpice in power electronics of a DC to DC converter shown here. If you have any questions, please don't hesitate to write me at chris.ionello@nasa.gov. Thank you for your time.